Hello there. It's Physics Coach Powers. Physical Science Coach Powers, anyway. All right. So today we're going to be talking about acceleration. Yesterday we learned about the other type of motion, velocity, and now we're going to learn about acceleration. So while velocity was a change in the distance over time with the direction, acceleration is going to be the change in a velocity over time. All right, sweet. It's also going to include direction. So here's our objective today, guys. You're going to love this. All right, so define acceleration, calculate the acceleration, and graph the acceleration of an object. Oh, yeah, nice and easy. Let's do it. Here we go. Acceleration, the rate at which velocity changes over time. Now, one of the cool things about acceleration is that if velocity changes based upon the direction changing, then you also have acceleration. So this is something that may blow your mind a little bit as you go further and further into it. Especially as you talk about centripetal acceleration, some of the cool things that are involved with forces, and it's just amazing stuff. But anyway, we're just going to hit the basics for right now, okay? So if an object changes its speed, its direction, or if it changes both, then you have an acceleration, okay? So acceleration must include direction. When you're writing out the answer for acceleration, make sure you include direction. Write the direction out. Otherwise, it's not really considered acceleration. Although, if you have the right units down, we're not going to be like, hey, that's not acceleration. But try to make sure you have the direction as well as units. All right, so acceleration can be a change in speed. I can increase speed or decrease speed, and I have acceleration. Now, sometimes we talk about the decrease of speed being deceleration. And that's a way that, if you decelerate your car, that means you're slowing down. And that's a fine way to talk about it in terms of your everyday life. But in science, we just basically say we have positive or negative acceleration. So negative acceleration is deceleration, but we don't really use the word deceleration. We at least try not to. We try to use the word acceleration that is negative, okay? Change in direction. So if a motorcyclist is riding around the inside of a large barrel, they're constantly accelerating. Why? Because zoom, 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 zoom. They're always changing direction, right? Constant acceleration. A person, if they're on a Ferris wheel, they're going to go this way. No, they're going this way. No, they're going this way. They're always changing direction. So a person on a Ferris wheel, even though they're going at constant speed, they are continually accelerating. Constant acceleration. What, Powers? Yeah, that's change in direction means you have acceleration. And if we have change in direction that is occurring in a circular motion, we call it centripetal acceleration. Centripetal. No, centripetal. All right. So acceleration is a change in velocity. Acceleration includes, fill it in, and it must write, okay, direction, right? They include the direction. Now, the units that we use for acceleration, let me get some pen work going here. I'm going yellow today. All right. Acceleration includes direction. So by golly, you better write direction. All right. So if we have east, then put east, toward the pole, whatever, in a circle. All right. The average acceleration over time interval can be calculated by dividing the change in the object's velocity by the time over which the change occurs. This is the formula you're going to use, but sometimes you'll see that formula broken down where the VF and the VI are all written out. So you might actually see this formula written out as VF minus VI over T. Now, VF, final velocity, VI, initial velocity. Okay, so acceleration, the units for that are in meters per second squared. And the velocity, remember, is meters per second. Okay, and then the time is second. Okay, so when you're coming up with an answer, over here, you're going to have meters per second minus meters per second, which of course is going to be equal to meters per second. And then you're going to divide that by time, right? So this is divided by time. And so this is going to be in seconds, right? So let's change that to seconds real quick. Just look at it in terms of units. And you know what? This is probably messing with your brain. Well, equals. All right, so meters per second divided by second. Guess what that's going to equal? That's going to equal meters per second squared, okay, per second. All right, so this is the way we come up with the formula for acceleration. Let's see if we can put it into practice. Let's talk a little bit more about calculating our acceleration, though. In our book, if we're talking about straight line motion, just going in a particular direction, positive acceleration means the object's velocity is increasing, and then a negative acceleration means the object's velocity is decreasing. We talked about that. And then our units we just talked about, you can think of it as meters per second or meters per second squared. Okay. Now think about it in terms of something falling. Okay, like the acceleration due to gravity, we're going to learn later on, is 9.8 meters per second squared. So if it's traveling, let's say 9.8 meters per second in second number 1, okay, then in second number 2, it's going to increase, right? And it's increasing by the same rate if we're talking about acceleration due to gravity. Now I'm actually giving you a slightly incorrect numbers here, but that's okay. We're just going to pretend for now. So then if I had 9.8 and then I had double that, then I'm at 19.6 meters per second. Okay. So I'm doing 9.8 meters per second, right? That's what that means. 9.8 meters per second. So if I go from 1 second to the next second, then I'm increasing the velocity by 9.8 meters per second. And if I went to the next second, then I'm increasing my velocity another 9.8 meters per second, right? And so 18, 19. Did I do my math right? Oh, my confidence. Yeah, it looks good to me. All right, so 29.4 meters per second. So you're just increasing 9.8 meters per second. Every second you're getting faster. That's the idea here. Okay, so let's look at a problem. Flower pot falls off a second-story windowsill. Flower pot starts from rest and hits a sidewalk 1.5 seconds later with a velocity of 14.7 meters per second. Find the average acceleration of the flower pot. So we're finding acceleration, and we got to think about what we're given: velocity and time, right? And so one of the things that and then the other thing that we are given, but you don't see that we're given, is this initial velocity. Because why? It starts from rest. So if you see that phrase, starts from rest, that means that it's starting at 0 velocity, right? 0 meters per second. And so we've got 0 meters per second as our VI, and our VF is 14.7 meters per second, and our T is 1.5 seconds. So now we just have to calculate acceleration. That sounds pretty easy. Our formula is VF minus VI divided by T. And so then we take and we get our 14.7 meters per second minus 0 meters per second divided by 1.5. So it's just 14.7 meters per second divided by 1.5 seconds. Yeah, I think you've seen this before. 9.8 meters per second squared. Now you'll notice that we have a direction there, down. Remember I said that you should always include a direction when you're dealing with acceleration. So here the pot is falling down, falling toward the ground. So you could say down, you could say, toward the ground. There's a lot of different ways that you could say that. So don't feel like, oh, I'm going to say the wrong thing. Unless it's like east, west, or north, and I say it's north and you say it's south, that's going to be wrong. But you can just basically talk about and describe the direction that it is moving, and you're going to be fine. Now, what does it mean to graph acceleration? So I love the graphing part of velocity, right? So, and I even talked a little bit about what does acceleration look like on a distance time graph. Well, now let's look at a velocity time graph or a speed time graph, right? We don't really have velocity because we're not showing the direction. But if we look at a speed time graph, we now can figure out what acceleration is in the same way that we did figuring out the velocity. We can look at the slope. The slope of a speed time graph is is acceleration, just like the slope of a distance time graph was speed or velocity, right? So let's look at this. Now, in this case, we have to kind of describe the motion we see. Over a period of 5 seconds, we are going from being 10 meters per second down to 0 meters per second. So we're slowing down, right? This downward slope means that we're decelerating or accelerating in a negative direction. We're getting slower, all right? Now, so on that top, you can see we're getting slower. And now look at what it would look like on the distance versus time graph. So these are the ones that I showed you last time. Remember how I showed you there was these curved lines? Well, a straight line in a speed time graph is a constant acceleration. But in this distance time graph, you can see that it was curving. It was changing its velocity. And so that was going to be a curved line. So this one is distance time. Okay, and it's a curved line for constant acceleration. But this one is speed time. And this is a straight line for constant acceleration. Both of these are considered constant acceleration, though. Isn't that cool? I love how graphs interpret math. All right. So, bus traveling on a straight road at 20 meters per second uniformly slows to a stop over 20 seconds. The bus remains stopped for 20 seconds, then accelerates at a rate of 1.5 meters per second squared for 10 seconds, and then continues at a constant speed. Graph speed versus time for 60 seconds. What is a bus's final speed? So now I want you to take this because it's so helpful to put this into a visual perspective, and it will help you understand acceleration. So I want you to just make a little graph. Okay, and I want you to try to graph what you are seeing here. All right, so we're going to pause it, and then we're going to come back and see how I did. Okay, pause it, and welcome back. So first of all, we have to determine our x and y axis. Now you've saw a few of these, so we probably want to put down our y axis being speed, and our x axis being time. Right. All right. So then we look at what that looks like. And that said, for the first 20 seconds, we go from being, actually, I'm going to change my color here because this is starting to hide out a little bit. So we start at 20 meters per second, right? And then after a period of 20 seconds, we've gone down to stop. And we've actually stopped, and we stop for a full 20 seconds. And then we speed up again. And in 10 seconds, we get all the way up to 15 meters per second. And then we keep at a constant velocity. So now our acceleration is a flat line. It's a zero acceleration. We're not accelerating at all. We're a flat line. Does that mean we stop moving? No. Here, we've stopped moving. Why? Because our speed is zero. So that's stopped moving. But here, we're still moving. We're just not accelerating. That's constant speed, no acceleration, but we're still moving at 15 meters per second. Does that make sense? Isn't that fun to graph? Did you guys do that? Did it look like that? I hope so. I think that you guys are pretty awesome, so I imagine you did it. If not, then make sure you ask some questions if you're not sure what's going on there, and I'll help you out. Okay? All right, so final speed. Can I read the graph to figure that out? Yeah, and again, you're just looking at where I'm at here, and I'm just taking that, and I'm pulling that line back to see where it intersects. So it's intersecting at 15 meters per second. Cool? All right. It was easy, right? Acceleration. We defined acceleration. We calculated the acceleration of an object using the formula A equals VF minus VI divided by T. And then we graphed the acceleration off an object. We got to see how that object works in real life on a graph, how the math turns into the graph, and the graph is real life, and it's just so much fun to see. And that's why I love science. I hope you do. Have an awesome day. Hey, be kind to one another. Because if you're not kind, that's just mean. And we're not going to be mean. We're going to be kind. Have a good one.